This is my second video log for my independent study working on the Gunship game engine. This week I worked on getting collision detection working with moving collidable objects, and I also spent a lot of time working on performance optimizations. First, let's demonstrate that moving objects work. Here I've got something similar to my just circle movement example, but I've got it working with collisions now. You can see some objects are sometimes marked with little white squares on the top. That means that there's a collision being detected for that object. And you can kind of just, well, actually, why don't I do a little frame by frame stepping? You can kind of verify visually that it is working. I still don't have proper unit tests going to confirm that my collision detection results are robust, because I've mostly been focusing on performance rather than correctness. But you can just kind of visually verify the things are all working as intended. We're only getting collision messages on things that are colliding, and if something's colliding, it is in fact getting a collision message. So I can get that running again. So this example that I've got going on right now is 1,000 objects in a 100 by 100 area. And if we look to the left, I'm spitting out the update time every frame, and it's kind of fluctuating between 1 and 3 milliseconds. Let me have to forgive my coughs. I've got a little bit of a cold. So that's not really great, but you'll notice, so when those longer lines are actually Gunship warning me that I missed the 60 frames per second target time. But for the most part, I'm actually hitting 60 frames per second. So with 1,000 moving objects being able to hit 60 frames per second, it's not AAA level, not really even indie level, but for like a small test game, anything that I'm going to be doing in the near future, this is at least a good start. So that's 1,000 objects moving around in the scene. For performance purposes, I've been actually testing with 10,000 objects in the scene. Why don't we just get that started? At the start, and 10,000 objects to me seems like a pretty good benchmark because it's just a lot of moving objects. It's probably more than I've ever needed in any of my small games. So I figure if I can handle running 10,000 objects per frame at 60 frames per second, I'll be in a decent shape for a while. Though you can see that right now, that with 10,000 objects, it's not close to 60 frames per second. Just by looking at it, you can see it kind of fluctuates somewhere in like the 40 to 50 millisecond range. That's actually about half the speed that it runs at when I'm not recording. Like when I'm not recording with 1,000 objects, it never drops below 60 frames per second, and it runs at about 25. It takes about 25 milliseconds to perform the collision tests with 10,000 objects. When I started at the beginning of the week, it did take around 55 milliseconds to do all the collision tests with 10,000 objects. And over the course of the week, I managed to drop that down to 25 milliseconds for the collision tests alone, or for the entirety of the update function, which is that performance is really dominated by, that's still like 90% collision detection. Major performance improvements included fixing a kind of nasty mistake that I made sometime a while back that was resulting in probably a couple dozen string allocations per frame. Once I got rid of that dropped the runtime by like 20 milliseconds. That was just a really silly mistake. That also cut down on memory usage a bunch. I also changed the hash function that was being used by the hash table implementation. The default hash function used by the Rust hash map that's in the standard library is a SIP hash, which is a cryptographic hash, which means it's a lot more robust than I need for just a game. So I switched it to the FNV hash, which is much simpler. I can actually open up that code really quickly. Um, the entire hash function is an XOR operation and then a multiply, a wrapping unsigned multiply with a constant value. So that's substantially faster. It took probably about 10 or 15 milliseconds off the collision detection time in total, because I did that in a couple of steps. Other interesting optimizations that I've done this week is the way that I was originally representing my grid cells the way I'm representing my grid is a hash map where the key is the grid cell, and then the value is a vector of all of the objects that are in that have been put into that grid cell. And originally I was storing the entity in there, and then when I was testing, so if I've got a new object and I'm testing, like, oh, it lands in this grid cell, let me test it against all the other objects that are in that grid cell. I would get the list of entities, and then I'd have to retrieve each of the colliding hierarchies for each of those entities. And so that was a bunch more hash lookups that was taking more time. So instead, I'm now just storing off a pointer directly to that hash, to that bounding object, which saves me a bunch of time. That took off, it looks like maybe 5 milliseconds total, which is a nice performance improvement for almost no change. And one thing to note about this is actually, like, this is the sort of thing you'd see pretty commonly in C++ code, where this goes back to my kind of secondary goal to evaluate the value of Rust, where this is very common in C++ code. Like, I do this all the time. You store off a pointer to an object, or to some object. That way you're not looking it up. But this runs into potential issues like pointer invalidation or iterator invalidation, where this pointer is actually a pointer into memory that's inside of a hash map. And if I were to, like, save this pointer off and then push more objects into that hash map could reallocate its backing store, and now this pointer is pointing to freed memory. And I ran into that problem several times when I was doing this in C++ last year. And one of the big bragging points for Rust is that you're not supposed to ever run into issues like that, because Rust doesn't allow you to just store off raw pointers to random points in memory. If you're using just the safe subset of Rust, which is the vast majority of what I'm doing here, you can't have that happen. You can never have null pointers. You can never have pointers to freed memory. But this storing a raw pointer or dereferencing a raw pointer in Rust is an unsafe operation. So I have to use the unsafe superset of Rust. So this would potentially go, like, at first blush, this seems like, well, Rust isn't effective. It's not, I can't do what I need to do with Rust. But really what's happening here is Rust is providing that escape hatch that I need. For performance purposes, I need to be able to do this lower level thing. I need to be able to store a raw pointer. And I can actually, in this particular context, I can verify by hand that what I'm doing is safe. And it's safe because to a large degree of what Rust is doing. Like, if I were doing the same thing in C++, it would still be possible for that pointer to be invalidated. But in Rust, because I actually have a reference to that, to the backing store, to that hash map that pointer is pointing into, it's impossible for any other piece of code in this thread or even in another thread to modify that hash map to push any more elements onto it. So even though what I'm doing is, according to Rust, unsafe, it's still a safe operation because I know it's never going to fail, because of the other guarantees that Rust gives me. So this is an interesting case where I can use unsafe operations in Rust and still know that they're safe because of some of the other guarantees that Rust gives me, which I think is a nice advantage and something that I couldn't do in C++, and an issue that it helps me skirt around issues that I have already run into multiple times when programming in C++, and have produced some pretty nasty and hard to fix bugs. One other, minor optimization that I did was checking if a collision's already been detected between two bounding volume hierarchies before actually performing the test. because if you have overlapping bounding volume hierarchies, they might overlap in multiple grid cells, and the first time that you detect that they're in the same grid cell, you'll detect detect the actual collision, and then add it to the list of detected collisions. And then the next time, if I don't early out here, I could wind up performing that test again, and that test could be very expensive. If it's like a mesh collision test, then that could wind up being a very expensive test to do. So this wound up, I didn't take a close note of this one, but this one probably wasn't a big gain in this case, but because right now the bounding volume hierarchy test is actually pretty cheap. I don't have mesh collisions. I only have, checking two AABBs, which is very cheap. That'll be a fairly important optimization down the line. So as it stands, I'm at about 25 milliseconds per frame to do my collision tests, and that's not great. I mean, it's okay for 10,000 objects, but my goal is to get down to at most 8 milliseconds for 10,000 objects, ideally down to 4 milliseconds for 10,000 objects. So I doubt I'm going to be able to do that without some form of concurrency, or probably and also maybe like a hierarchical grid, which I'm kind of at this point expecting to have to go into. But I'm at the point where I'm like trying out different changes, and I'm like tweaking my code to see if it'll make it any faster. And it's actually very hard for me to tell if my changes are making a big difference. As you can, like if you take a look at just what some of this output from a previous run, you can see that I get a pretty large amount of variance in the update time. Like the update time can vary from like 44 milliseconds up to like 55 milliseconds or like 56 milliseconds. And it's like sometimes it can drop low. Sometimes it could be 39 milliseconds. It goes up to like 51 milliseconds. And that variation makes it hard for me to tell conclusively if my changes are making things better, if they're not having an impact, or sometimes they could be making things worse. And it becomes hard. It's becoming difficult for me to tell what's going on. So one of the things that I put together, what happened there? Okay. One of the things that I put together early on was I put together this, let's do stopwatch. Here we go. So I put together this stopwatch functionality. And if I want to actually demonstrate it, what I do is I can create a stopwatch object and in any scope anywhere in my code. And usually I just put it at the top of a function. And I give it some text that's supposed to identify to me when I'm looking at the results what's going on. So for my draw function, I put in draw. For the update function, I put in update. And then when the stopwatch object is created, it marks off the time, the point in time when it was created. And then when it goes out of scope and is destroyed, it times how long it was alive, and then stores a record of how long it's alive. And actually right now it's printing out that data. So this information that I'm getting right here, this update time taking 49 milliseconds, that's coming from this stopwatch that I'm creating right here. And this is on top of printing out to the console. This is also printing out, you don't get to see it, but it's printing out here to stopwatch.csv. And if I open that file up, you can see that it just prints out the CSV file with a record for every frame, effectively. And normally what I'd be doing is I'd be printing out a record for how long the draw time takes and how long the total loop takes. And then I can open that up in Excel, or I usually do it in Google Sheets online, and I can upload that data, and like Google Sheets will help me do some statistical analysis on that data, and I can get information on what my average frame time is, what my standard deviation is, and that's been pretty useful so far. But that's really slow to do because every time I run it, I gotta make sure I upload it. I gotta do a little bit of cleanup on the data because the data's got a lot of outliers and it's not well formatted. It's just all the information's thrown together in one file. So I've been starting to explore other ways to get accurate performance data so that I can more directly target performance improvements. And as an aside, I still have Intel VTune. I can still open up my executable in Visual Studio and run VTune on it, and I can debug it the same way that I would before. Rust has kind of mostly working debugging support in Visual Studio at this point. At least you can set breakpoints and you can step through your code. You can't look at variables at runtime, which is pretty annoying, but I don't need that functionality to be able to do VTune. But the problem with VTune is it doesn't tell me the amount of time I'm spending. It doesn't give me a really good... It doesn't give me targeted information about the specific things. I can't get information on like how long the draw function is taking relative to how long the update function is taking, and how much of the update time is being spent in collision detection versus updating the scene graph versus doing other stuff. So I'm trying to figure out a way that I can get that information in a more targeted fashion. And one of the things that I'm trying out is Rust comes with a benchmarking tool, or it's got this kind of unstable benchmarking tool on the nightly builds, which is what I'm using. So I've got it set up, and if I run cargo bench, so I normally do cargo run to be able to run my code, but if I do cargo bench and I hit that, and it'll take a second. It's got to recompile my code. But if I go, let's see, where is it? Shaders, lib, should be in our test. Here we go. So when I do that, it's gonna, I can define this function. I call it it's my collision benchmark. Oh, and here we go. You can see it going on. It's opening and closing a bunch of windows really fast because it's actually starting the game engine. Well, you can see what it's doing here is it creates a game engine, sets up the scene the same way as it does in the other one, where it's creating right now 1,000 cubes. It's giving it a random position and then a collider. And then it's inside of this iter function, you actually give it a closure, and then inside this closure you do all the stuff that you care about doing for your benchmarking purposes. And so I've just got a special function here where all it does is it just runs the collision update. So I'm just getting benchmark information on my collision update. And the reason why you're seeing windows open and close really fast is it's creating a full instance of the engine, which includes opening a window, creating an OpenGL context, creating a renderer, loading in resource files, like all this spew that it spits out at the top. Like you can even see here, it's like, oh, it's telling me the OpenGL version because it's trying to start an OpenGL context. And that's one of the things I'm going to need to do in order to get better performance data is, to do better benchmarking, is to be able to create a benchmarking test harness where I don't have to create a full instance of the engine. I just create enough state data to be able to test a particular portion of my game or of the engine, and then just test that engine or that portion of it. That's neither here nor there. So the output of the benchmarking function that Rust provides is the total, like the average nanoseconds per chunk that you actually care about, and then the variance on that. And so you can see, since it's spitting out nanoseconds, you can see that update that's doing, the time it takes to update 1,000 non-moving cubes, because that actually isn't the collision detection performance is the same if the cubes are moving or not right now. So the time it takes to do collision detection on 1,000 cubes is 6.5 milliseconds, which is slower than I like, but at least this is a well tested number. Like this is tested over multiple instances of the engine and over multiple iterations. And it also tells me my variance is 3.7 milliseconds, which now I can see very clearly that I've got pretty wild variance in my time. That's like 50% variance, which is crazy. And this number, this is good. This is certainly an improvement over just running the game and looking at the output, or having to load a CSV into a spreadsheet editor and start doing some analysis on it. Like, doing all that's really annoying, and this is a big improvement. But this data is kind of too high level. It's telling me, the total time, and I've got to do a bunch of hacky work to get this working. The better solution would be able to just run the game as usual, just like the same way I would any other time, and be able to get this information, from a normal run. Like, I run my game, and then when I close my game down, it just at the end spits out the same information to me. And what would be even better than that, if I could get kind of nested information as well. Like, the total time is 6.5 milliseconds, and 3 milliseconds of that is drawing, and 2 milliseconds of that is collision, and under collision, like, some portion of that is doing the grid collision, some portion of that is actually testing. It's spent doing individual tests. And so excuse me. And so that's what I'm gonna do. That's what I'm starting to do, and I'm gonna do that probably for most of next week before I go back to doing feature work. Is I'm gonna start adapting this stopwatch library that I was working on before. I'm gonna instead of just taking a flat list of all of these datas and spitting out a CSV, it's gonna start. I'm starting to set it up so that it takes a hierarchical. It tracks the call stack as you create new objects, or as you start stopwatching new critical sections, and I'll keep track. I'm gonna keep track of all of the each time you run it, and probably try to keep track of frame boundaries, and then at the end, when I close down the game, I want it to spit out a little chunk of whatever out to the console that shows me like a hierarchical view of the entire engine, with average time spent in each function per frame, and the variation on each of those, so I can see like maybe if it's just one thing, like if it's just the draw function that's causing a lot of that variation, or if it's just the collision detection that's causing a lot of variation in my frame. I'll be able to see that, and I'll be able to see which area is spending a lot of time, and that'll be really useful as I start to do more of these optimization things. Because if I were to change the way that I'm representing the collidable objects in memory, that could be a performance boost in one area, and then that could slow things down in another area. And right now, I don't have any good way of detecting that and measuring those changes. I can only really measure overall performance. So hopefully getting the system set up will allow me to, one, it'll allow me to get more specific data on specific areas, and two, since it's a manual instrumentation, since I have to specifically say this is the area that I want to time, and this is what I want to mark it as being timed as, it'll allow me to just focus on the areas where I care about performance, and not waste time, not waste any performance instrumenting or trying to measure time on parts of the code that I don't care about. And that'll hopefully turn into, over time, as I work on it and add features to it that I care about, that'll turn into a much more robust instrumentation tool that I can just have always on profiling of my code, where I just running my game normally. If I'm running it, it's still doing that profiling. It's still telling me how long stuff is taking. And if I'm just say if I'm just running my game and suddenly there's a lag spike, I can shut down my game, take a look at the info that's printed out, and I can see exactly what took longer on those particular long frames, which will be a really useful infrastructure going forward, and something that I can get started on pretty easily right now, and it'll help me with my current task. But so that's it. That's what I worked on for this week. Holy crap, this video is 25 minutes long. I'm not recording it again. All right, bye.